Welcome to my YouTube channel. Please subscribe. Today we are going to look at a Poisson distribution. So a Poisson distribution has conditions. One, you must know that events occur singularly, at random, independently, and at a constant rate. And you will always know that actually this question is about Poisson, because they will always tell you how events are occurring at a particular time and at a constant rate. So a Poisson distribution follows, if a random variable follows a Poisson, it only has one parameter. For example, that parameter can be referred as the parameter of Poisson. It can be referred as mean, or it can be referred to as average. Here are some of the examples of the Poisson. For example, computer breakdown occur at an average every 8 days at an office. Meaning after every 8 days, a computer will break down. That's what it means. Every 8 days. So meaning if I am talking about 16 days, you automatically know that actually 2 computers broke down. Another example could be people arrive being at an airport at an average rate of 3 persons per minute, meaning every minute 3 people arrive. Then also we can have internet gets disconnected on average every 48 hours, meaning every 48 hours internet will get disconnected. Every 48 hours, meaning when we talk about 96 hours, you'll know that internet will have gotten disconnected like twice. So you need to look at the question and tell that actually this is Poisson. So here is the formula for Poisson. If a random variable follows Poisson, then probabilities can be worked out using this very formula. The probability of x equaling to small x is equal to e negative lambda x over x factorial. So the lambda is the parameter I told you about. Then this x can be from 0 up to infinity. So meaning Poisson is an infinite distribution. It can like an event can continue up to infinity. Other things you need to know is about the mean. How we calculate mean for Poisson. For mean, it is the same as the lambda that you have. Also, the variance is the same as the lambda. If you want standard deviation, it will be root of variance, which is lambda. Then when you come to the mode, a Poisson distribution has 2 modes. We are going to look at 2 cases where lambda is an integer. So if lambda is an integer, then that Poisson distribution will have two modes. That is lambda and lambda minus 1. So for example, if we have 5, then the mode will be 5 and 4. Then if lambda is not an integer, that is case 2, then our mode will be the value before that lambda. For example, if it is 8.9, then the mode is 8. Some of you might want to round off, but that's not the way it is done. So if you have 8.9, it is the value before the integer before 8.9, which is 8. 3.1, the mode will be 3. So you need to know that Poisson has 2 modes. So let's get used to working out questions on Poisson, getting used to the formula if you're seeing it for the first time. We said this is our formula. So if this is a formula, then how do you get used to it? If, for example, if they ask you probability of x equaling to 0, wherever there is x, you will always, like you put a 0, and the lambda is given in the question. So it is simply E negative lambda. Because if you make your x to be 0, the whole of this will be 1, and then you stay with E negative lambda. And then when x is equal to 1, when you substitute your lambda as 1, you end up staying with that. Then when we ask for probability of x less than 3, less or equal to 3, it means we are interested in all values less than 3, 0, 1, 2, and 3 is also included. And when you substitute it in the formula, it is like that. But when you look at the formula, you see that every formula has E negative lambda. So you can pull it out. So when you pull it out, and if you have lambda to the power 0 over 0 factorial, it is actually 1. So when you pull it out, you end up having to, work in with this kind of expression. And it is very easy to work with. So you can see that in Poisson, all you need to know is the lambda. And the lambda it is very important for you to know how to work with it. It is very important for you to know how to work with lambda. It's very important. If they tell you probability of x greater than 3, it means 3 is not part. We want from 4 to infinity. But remember, it will be really lengthy. You can't work from 4 to infinity. So the shortcut is 1 minus probability of 0, 1, 2, 3. So we have to know the total probability at the end of it all is 1. So to get from 4 to infinity, it is basically 1 minus probability of 0, 1, 2, 3. And this is it. So meaning you just have to know your lambda and substitute in this kind of expression and then get your answers. Then when you talk about linear combination of two Poisson variables, there's when they can combine two variables in one question. For example, they tell you the random variable x represents maybe internet breakdown, and they tell you maybe they break down at a constant rate, maybe of 1 every 8 hours of use. Or they can also combine, like internet. And then they tell you that every 48 hours, the internet breaks down. So they are combining two variables in one question. So how do you get your lambda? You add the lambdas, because we've seen the only parameter we need to know in Poisson is the lambda. Lambda, which is the mean or the constant rate at which something is occurring. So the lambda, if two variables are combined, is the sum. So here is the question. So one thing you need to know is that you need to be very careful with units of lambda. Very, very careful. Because we've seen the only thing we need to know actually in Poisson is the lambda. The lambda, in most cases, is given in the question, but the questions below it might want you to manipulate the lambda or, change it or have something different, but still with the lambda. So here is the question. I hope they are visible. Okay. Computer breakdowns occur randomly on average once every 48 hours of use. So meaning we are told that every 48 hours of use, one computer will break down. So they have given us the lambda in the 48 hours. So the question says, calculate a probability that there will be fewer than 4 breakdowns in 60 hours of use. So we are told fewer than 4. It means we are looking at probability of x less than 4. And now we see that the lambda is changing. According to the question, we were told that 1 in 40 in 48 hours. But here we are told 60 hours. So we need to know those computers. How many computers will break down in 60 hours of use. So we were given that actually it is one that breaks down in 48 hours of use. So I'm going to work it out here. Okay. So mean, which is the lambda, and then the hours. So we are given that one computer breaks down in 48 hours. So we need to know in 60 hours how many computers will break down. And when you cross multiply and find your lambda, you end up having 48 lambda equaling 260. And the lambda will be equal to 1.254 for 60 hours. So now the question was asking us to find the probability that fewer than 4, meaning probability of x less than 4. This is where we have probabilities of 0, 1, 2, and 3. If you have memorized how to work with Poisson, it is simply E negative lambda. Then we have 1, the one of 0, then for 1, for 2, lambda squared over 2 factorial, for 3, lambda cubed over 3 factorial. So you just have to substitute, and we shall end up having E negative 1.25, and then we say 1 plus lambda 1.25 for 1 over 1 factorial plus 1.25 2 over 2 factorial plus 1.25 cubed over 3 factorial. So when you work it out, you end up having your final answer as 0.962. So you needed to be very careful with the lambda, because the lambda keeps on changing as you move on into the questions. And then next, we go to question 2. It also originates from question 1, so you need to know that. So we are told that independently of the computer breaking down, the computer operator receives phone calls on average twice in every 24-hour period. So they are combining computer breakdowns with a computer operator, receiving phone calls. So and I remember telling you that when there are two variables of Poisson that are combined, then the lambdas, we add them up together. So the question says find the probability that the total, you need to be very careful to this, the total number of phone calls and computer breakdowns in a 60-hour period is exactly 4. We already got the lambda for the computer breaking down in the 60-hour period. So we need now to work out the lambda for the computer operator in 60 hours. So for the phone calls, if the random variable is y, so this is part 2. Then for the phone calls, we have the mean, and which is the lambda, and then we have hours. We are told that on average 2 every 20, so meaning we have 2 receives 2 in 24-hour period. So we need to know what will be the lambda in 60 hours time. So when you work it out, you end up having 120 equaling to 24 lambda, and when you calculate your lambda, it is going to be 5. So total. So we are going to get the lambda that we have to use, because we are told there are 2 events, 2 Poisson events that were combined. So meaning even the lambdas, we shall add them up together. So the lambda, if I have x and y variable, and they follow Poisson, then we add their lambdas, which is 5 plus 1.25, and I will have my new lambda as 6.25. So this is what I will be using in answering the question. So the question says that find the probability of the total number of phone calls and computer breakdowns is exactly 4. So probability of x equaling to 4 is going to be E negative lambda, and the lambda we already know it as 6.25. Then lambda 6.25 power of 4 over 4 factorial. So when you work it out, you end up having your answer 0.1222735, and you can give your answer at 4 decimal points, and you give your answer as 0.12227. Yes, so that was all about that question. So we got approximations. These are very important. When it comes to Poisson, we look at approximations, and you must know the conditions to why you use one distribution to work out a different distribution. So we are going to start with a binomial to Poisson. A binomial question, but we are going to answer it using Poisson. You need to be very careful. It is a binomial question that we are going to work out using Poisson. So a binomial question, and you must know what we must have in binomial, and then what must we have in Poisson. So in binomial, you have n and p. So we've seen that if the question is binomial, and then the n is greater than 50, and the probability is less than 0.1, then you use Poisson. So it is a binomial question that we are going to answer using Poisson. So now, since it is a binomial question and we are answering it using Poisson, and in Poisson the only parameter we need is lambda, which is the mean. So it means the mean this time around that you will use in the Poisson expression, the lambda that you are going to use will be the NP, because the question was formally binomial. And we said in this case of a discrete, because the binomial is a discrete experiment and Poisson is a discrete experiment, so the x is left the way it is. So there will be no need for continuity correction. That is what you have to know. Then another approximation that we look at is the Poisson to normal. It is a Poisson question, but we are going to answer it using normal. So the condition is that the lambda must be greater than 5. So since in Poisson, the mean is lambda, variance is lambda, and when we are working out with the normal, remember we standardize. Remember we use z equaling to x minus mean over standard deviation. So it means that the x The mean will be the lambda, because it is actually for Poisson, and then the standard deviation will be root of lambda. And we see clearly that this x, since it is discrete, that we are working out, but we are using a continuous. It is a discrete experiment that we are going to work out using normal, which is continuous. Then we do continuity correction. The x you're given in the question shouldn't be the x you use. You either add 0.5 or subtract 0.5. So in continuity correction, if they give you greater than 41, you need to know 41 is not part, so you add 0.5. If they say greater or equal to 41, 41 is also included. So to have it included, you consider 40.5. Less than 41, it is not part. We take 40.5. Equal to 41. In continuous, we don't have equal to. So what you do, in this 41, you add 0.5 and subtract 0.5. Yes, discrete experiments, they take on particular values, but for continuous, the probability of taking on a particular value is actually 0. But if we are doing continuity correction, this value that you're given, we give it in terms of like a bound. You add 0.5 and then subtract. So let's work out this question. The number of goals scored per match by every lover is represented by a random variable x, which has a mean. So we have a mean. So we're saying set two conditions for x be modeled as a Poisson distribution. We looked at the conditions. They must occur singly, at random, independent, and a constant rate. So any that you put would be right. Then I think assume now that x follows Poisson. Here they had not told us actually whether it follows Poisson. Yes, so this is the lambda they have given us. So one probability of x. We want the probability between 2 and 6 basically. So meaning we shall have to consider 3, 4, and 5. The probabilities of 3, of the 4, and the 5, and then you add them up together with a Poisson. So okay, answering part 2. Probability of 3, 4, 5. This is simply E negative lambda, which is simply 1.8. When I come to the 3, it will be lambda 3. 1.8 cubed over 3 factorial plus 1.8 power 4 over 4 factorial plus 1.8 5 over 5 factorial. You work it out and get your answer as 0.2590. Always give your answers to 4 decimal points. And then they are saying that the manager promises the team a bonus if they score at least 1 goal. So we need to get the probability of getting the bonus. The manager promises the team a bonus if they score at least 1 goal. So we need to first get the probability of scoring at least 1 goal. So part 3, it is simply probability of x greater or equal to 1. So you remember this being a Poisson, it runs from 1 to infinity. So the shortcut would simply be 1 minus probability of x equaling to 0. So when you work it out, you end up having 1 minus e negative lambda, which is 1.8. 1, because if you have lambda to the power 0 over 0 factorial, it is 1, and you end up getting your answer as 0.8347. This is the probability for scoring at least 1 goal. So if you scored at least 1 goal, you'd get a bonus. You need to read these questions carefully. The manager promises a team a bonus if they score at least 1 goal at least 1 goal. Okay, that's what I've answered. At least 1 goal. So this is the probability of scoring at least one goal. So if they say at least one goal in each of the next 10 matches, so this one, they have given us actually the n. So for 10, this is for just one goal, maybe in one match. Yeah, for one goal, this is for one match, a bit of scoring one goal in one match. So if I go for 10 matches, think of this as being a binomial question. Think of this as being a binomial question. So probability of x equaling 2 to 10. So it means out of the 10, if you still remember how to use the binomial question, probability of scoring 1, then power 10, then failing, get 1 minus 0.8, 347, you end up having 0.1653 power 0, and work it out as 0.1642. So you're saying the manager promises the team a bonus if they score at least one goal in each of the next 10 matches. So it is important that you first get a probability of scoring a goal in one match using Poisson. And when you get it, if in one match, then you can imagine 10 matches, it would basically be this value to the power 10. That would have been the shortcut. So if in one match it is that, then in 10 matches it would be that, and you end up getting you get your answer. Okay, so here is the question. Customers arrive at an inquiry desk at a constant average rate of 1 every 5 minutes. Set one condition for this to be modeled as a Poisson. So you must remember the conditions. They occur singly, at random, independent, and at a constant rate. Okay, we go to part 2. Assume that a Poisson distribution is a suitable model. Find the probability that exactly 5 customers will arrive during a randomly chosen 30 minutes. You need to be very careful with the lambda. That's what we talked about. You need to be very careful with the lambda. So, to answer that, from the question above, from the original question, we were told that they arrive 1 every 5 minutes. So if I'm to change the minute to 30, then the lambda changes. So when you cross multiply, you end up having your lambda as 5 lambda. Hold on. 1 every 5 minutes. Very good. 1 every 5 minutes. So if I'm to get my lambda, I end up having my lambda as 6. So they are saying probability that exactly 5. So probability of x equaling to 5 is simply e negative lambda, which is negative 6. Then for 5, it will be 6 to the power of 5 over 5 factorial, and you end up having your answer as 0.1602. 16062 as your answer. Then part 3, find the probability that a fewer than 3 customers, so probability of x less than 3, we would be looking at this probability of 0, then 1 and 2. So we are told that fewer than 3 customers will arrive and during a randomly chosen 12-minute period. You need to be very careful with the lambda because we are told 1 every 5 minutes, meaning 12 minutes. You need to be very careful. Sometimes they can even put in hours, so you need to be very careful with the lambda and its units. So when you cross multiply, you end up having your new lambda as 2.4. So you come and substitute you'll come and substitute, and you end up having E negative lambda, and then 1 plus, when I go for 1 to be 2.41 over 1 factorial, when I go for 2 to be 2.4 squared over 2 factorial, and when you work it out, you end up having your answer as 0.5697. As simple as that. And then we go to Roman 4, find the estimate. So when you see an estimate, just know we are looking maybe at approximations for the probability that fewer than 30 customers. So probability of X less than 30 will arrive during a 2-hour period. We need to first change the lambda. So if 1 is in 5, what of, when we talk about 2-hour period, 2 hour, remember we're given 5 minutes. So now when you change 2 hours in minutes, what do you get? 2 hours, when you change it in minutes, it is actually 120. So you need to be very careful. And then lambda, and then you end up having your lambda as 24 when you cross multiply. So look at where we used it was a Poisson, but we used normal because the condition is that lambda must be greater than 15. So if you were to work it out, you'll end up having this is our lambda, which is greater than 24. So I'm going to use the normal. So probability of X less than 30. 30 is not part, so I will take 29.5. You need to be very careful with that. So the X is 29.5. So I'm going to use normal. So, and remember in normal, Z is equal to X minus mean over standard deviation. So the X is going to be 29.5. Then the mean, remember we said the mean is lambda, and the lambda is 24 over root of 24. Because the mean and the standard deviation we use for Poisson. So this is going to be probability. When you work out this, you end up having 1.123 probability. So we can easily read this. This is simply probability of Z less than 1.123. So the normal table reads to the left, and you can easily read this on the normal table. Go to 1.12, and then go to where there is a 3, and then you add. According to what I have, we have a 6, and then when you add it to the end, you end up having 0.8692 as your answer. So you go to the normal table, look for where we have 1.1, then go to a column of 2, and there is 0.8686, then you go to 3, there is 6, and when you add it, because remember we add at the end, you end up having that as your answer. So you needed to know that very carefully. And then okay, here is another question. A random variable X has a distribution of Poisson with mean, that is the mean. The random variable R is the sum of the 3 independent values of X. So you can imagine you have X, you have X, you have X. Remember, you need to be very careful when you're reading these questions. The random variable R is the sum of the 3 independent values of X. So you can imagine the sum, here we have 3 independent values of X. So we have X, we have another X, we have another X. And each X has the mean of 1.6, 1.6, 1.6. So you can easily get the mean of 3 of them, which is 3 times 1.6. So actually it is R. We told the random variable R is the sum of 3 independent events. So if I want the lambda, then I will the lambda will be 3 times 1.6, because each one has 1.6. Remember, sum of 2 independent values. So they are same probability of X less than 4, R less than 4. So less than 4, probability of X less than 4, they are saying R. So it means we have 0, then we have 1, 2, and 3. So you just have to come and substitute in the Poisson experiment, distribution formula, which is E negative lambda 1, that is for 0, then for 1 it's 4.81 over 1 factorial, for 2 4.82 over 2 factorial, for 3 4.83 over 3 factorial. And when you work it out, you'll get the answer. Then question 2 says the random variable is the sum of the independent values of x. It is given the random variable is the sum of n. Is the sum of n independent values of x. So we don't know. You can imagine you have x's that are very many. So you can imagine you have one x, you have another x, and they continue up to n. N times. I can say maybe xn. So we do not know how many they are. So if I want lambda, how many are they? They are n. The x's are n, so it will be 1.6 then times n, which is 1.6n. So this is the lambda that you'll be using. And then so we are going to substitute here probability of the sum equaling to 4. It is simply E negative lambda, and the lambda is 1.6n, then 1.6 n, which is a lambda to the power of 4 over 4 factorial, is equal to 16 out of 3 times probability of the sum equaling to 2. So if the sum is equal to 2, we shall say it is E negative 1.6n, and then bracket 1.6n 2 over 2 factorial. So you can see clearly that this and this is appearing on both sides, and then you can work it out. You can divide both sides by 1.6n. So I'm going to say, so here your algebra really matters a lot. I'm going to divide by that both sides, 1.6n squared, so that I remove it from here, and when I close here, then we shall keep with 2 of them. 2 equaling 2, I can take the 4, I cross multiply it there, which is going to be 4 factorial times 16 over 3 times 2 factorial. And when you work it out, you end up having 1.6n squared equaling to 64, and you'll have 1.6n equaling to 8, and your n will be 5. So you needed to know here what your lambda would be, because we are told that it is the sum of n independent values of x. So if x, so you can imagine we had very many x's and n times. So you needed to know that each one has a lambda of 1.6. So for n of them, it would end up being 1.6 n. So then the next question, still on that very one, it is Roman 3. The random variable t is the sum of 40 independent. So meaning you can imagine you have now 40 of them, meaning the lambda would be 40 times 1.6. So the lambda here, because there are 40 of them, it would be 40.16, and we end up having 64. And then so you can say the lambda here is actually greater than 15. So meaning we shall use normal to work out this. Remember, the condition for using normal to approximate a Poisson is when lambda is greater than 15. So here we see that lambda is something very big. So we are going to end up doing what? We are going to end up using the normal distribution. So, and remember, the mean is lambda and the standard deviation is root of lambda. So, and the x, we do continuity correction. So I will say z is equal to 75.5 minus mean, which is 64, over root of 64. End up having z as 1.438. And remember, because we had greater, so I want area to the right of 1.438, which is simply 1 minus phi of 1.438. And when you read it, you end up having 0.9247, and your answer as 0.0753. So this is all about Poisson. If you've not subscribed, please subscribe, yeah, for more.